Hello everyone, my name is Haydar. Today I'm going to present for you the LPOD workflow scheduling algorithm that is implemented in the data view workflow system that works on the for the big data workflows. So before going too deep, let's give you some outline of the presentation. So I'm going to define the problem here, then provide some solution for it, and give some idea that how these solutions are going to work on the architecture. The algorithm that is going to be presented today is does have some preliminaries, and it consists of multiple algorithms that combine together that brings a planner for the scheduling under the workflows. And finally we are going to evaluate this algorithm among the other algorithms for a specific scientific workflow, and then at the end I will give you a summary of all. So this lecture is originated from the original LPOD paper named under a local path based optimized scheduling algorithm for deadline constrained big data workflow in the cloud. The LPOD algorithm, you can find the LPOD algorithm in the data view system under the workflow planner underline lpod.java file. So our problem here is that let we have a deadline and we want to find a schedule SCH that minimize the monetary cost while satisfying the deadline for us. So one of the solutions over here can be each of these bullets and a combination of these bullets. So we can distribute the deadline on each task as a sub deadlines. Then we can identify the partial critical path. Then we can assign each partial critical path under the cheapest virtual machine available, which is going to satisfy the sub deadlines. And then we should apply again the algorithm to adjust the ESD, EFT, LFT for related tasks. And what are these parameters? I'm going to explain more about them along the presentation. So we have an architecture for the workflow systems. The LPOD is going to be at the planner level. So for workflow system we need planners. As you can see in the previous presentation, I put some presentation about the ICPCP algorithm. The LPOD is another scheduler algorithm that can schedule for us our workflows. So for example, think that we have a workflow like alpha, beta or gamma, whatever. For example, word count, knife base, ANN, anything can be a workflow. The workflow is something that you can split it into some tasks, okay? So it needs some workflow engine, and then it will be split into some tasks executor, and under the virtual machines, different virtual machine or the same virtual machine. So by definition, the workflow as a parallel high-performance computing model nowadays has been broadly studied and used to orchestrate different computation tasks involving the complex data dependency in various researchers domains, such as, for example, these beta, alpha, and gamma can be like the astronomy, biology, seismology, and medical care and big data analysis. And again, a workflow for a workflow we need some pre-requirement. But what is a workflow contained of? Okay, the workflow is typically represented as a directed cyclic graph in which nodes represent the tasks and the edge represent the data dependency between two consecutive tasks. But here in the modern workflow management system, for example, this data view that I'm representing in it, facilitate and automate the complex execution process of the workflow on top of a high performance computing platform through a user-friendly interface. Okay, so what is this platform? Suppose that we have a cloud computing environment. How we define a cloud computing environment? A cloud computing environment is a we can define this environment with a multiple tuples like that has consists of VMT, VMC, vprice, VMI, type, DTR, dprice, boot delay. And if we have all of this parameter in an environment, we can call an environment a cloud computing environment. Okay, what is VMT? VMT is a set of VM types, virtual machine types, in the environment. And we can say that the case VM type is denoted to the VMK, which is the case of the virtual machine type. We can demonstrate the case virtual machine type is denoted the VMTK. VMC is a function from virtual machine type to real numbers, positive real numbers. It is the capacity function. And so we can say that VMC of virtual machine type virtual machine type something, the case virtual machine type. It is the computation speed of the VMTK in terms of million instruction per second, that we call it in abbreviation just MIPS. The R plus is the set of all positive real numbers, and the V price is another function from the virtual machine type to the positive real numbers. That is a virtual machine price function. And the virtual machine price function returns the monetary cost per each billing cycle, that we call it L, for using a virtual machine instance of type virtual machine type. VMI is a set of virtual machine instances, is a set. So it is a set. An individual virtual machine instance is denoted to VMI, the mth VMI. So the type is a function from virtual machine instance to virtual machine type. It means that a virtual machine type function and the type of the virtual machine instance of I instance, the mth virtual machine instance return the virtual machine type of instance, VMIM. DTR is a function from a Cartesian product of the VMI to a positive real number, that is the data transfer rate function. Data transfer rate function needs two VMI virtual machine instances like M1 and M2 that returns the network bandwidth between the instances, virtual machine instances. The D price is the data transfer price function, that is a function from the Cartesian product of the virtual machine instance to R plus. And the D price returns the price in dollar per megabyte for transferring data from a virtual machine instance M1 to virtual machine instance M2. And finally, the boot delay, that is the last parameter of a cloud computing environment, is the delay for a virtual machine instance before it becomes available after being provisioned. After defining the cloud computing environment, now we can define a big data workflow. What is a big data workflow? A big data workflow is another tuple that we can define it with W of T, D, T size, and D size. The T is a set of tasks, and the D is a subset of the Cartesian product of the T, that is the set of a data dependency edges between the tasks. We use the Dij to denote the data product that is produced by a task I and consumed by task J. T size is a function from task to positive real numbers, is a task size function, and the task size function of task size of Ti returns the size of task Ti in terms of million instructions. D size is another function from D to real positive numbers, and that is the data product size function, and the D size of Dij return the size of data products in terms of million bytes. Workflow graph. So here it was the big data workflow, and now we are going to define the workflow graph. Workflow graph is a table of T, D, ET, DTT, DTC, and the T is equal to W times T, the union set of the W and T, where the WT denotes the task set of W, and we add a task entry and task exit to the task sets. The WT, so the WT is the task sets, and the D is the union of the task sets and the D entry and the D exit times and the D entry is the D entry and I, where the TI, the task I, belongs to the entry tasks from the set of W, and the T exits is a T from task J to the exit, and the TJ belongs to the exit tasks. ET, that is the Cartesian product of the task and the virtual machine type to a real number, real positive numbers, is the task execution time. And the task execution time of the task Ti, a function of the task Ti on the virtual machine K, it is the execution time of the task Ti on virtual machine instance of type VMTK, which is defined that ET is equal to the task size under virtual machine cost, virtual machine type cost, and the execution time average is that is from task to R plus is the average task execution time function, which is defined as for example, execution time of task Ti average is the average is the sum of the execution time of the task on different virtual machine type under by the number of the virtual machine types. DTT is the data transfer time function, that is the product of the D virtual machine instance to the R plus, which is the DTT is a function of Dij. It means a task from virtual machine I to virtual machine 2, from virtual machine 1 to virtual machine 2, that returns the time for transferring task Dij from virtual machine M1 to virtual machine M2, which is defined like this. It is equal to 0 if the M1 and M2 is equal. It means we are transferring the data in the same virtual machine, and if it is not the same virtual machine, it will be the task size Dij under the data transfer rate between the instance of the virtual machines. Average data transfer time is a function from the task to the from D to the R plus, which is the average data transfer time function, and the average data transfer time function is defined as the task size under the average data transfer rate, as we defined previously, and data transfer rate among the C is defined by the summation over all of the virtual machine instances, where V1 belong to virtual machine instance and V2 belong to virtual machine instance, where V1 and V2 is not equal, the data transfer rate between V1 and V2, let's sum all of them, and the number of the virtual machine instance times the number of the virtual machine instance minus 1 by 2 is the average data transfer rate. So what is a schedule? What is a schedule? The schedule is defined with T, V, a virtual machine instance, M, AST, AFT, provision, and deprovision. So the T is the set of the tasks in a workflow W. Thus the T is equal to the WT in the previous slide. And the VMI is the set of the virtual machine instance in the C. Thus the virtual machine instance is equal to the C times the VMI. M here, the M here is a function from the task to the virtual machine instance, that is the task assignment function, and the M of Tij is return the actual start time of the task Ti and the virtual machine instance VMT. AFT, that is a function from task to the R plus, is an actual finish time function, and the actual finish time function of Ti returns the actual finish time of task Ti and the virtual machine instance MTI. Where prov is a function from virtual machine instance to the R plus, is a virtual machine instance provisioning time function, and the prov of virtual machine instance M return the time that virtual machine instance VMI M is to be provisioned. The deprovision of the is a function from VMI to R plus. Is a virtual machine instance deprovisioning time function, and the deprovision of VMI of M return the time that the virtual machine instance VMIM is to be deprovisioned. The total execution time and monetary cost of the schedule SCH are defined by workflow makespan and workflow cost respectively. So what is a workflow makespan? We call it WMS. Suppose that we are given a workflow schedule SCH. The makespan of workflow SCH, we can define it like this: the SCH of the actual finish time of the SCH times T of exit. And the workflow cost, that we call it WC. Suppose that we given a workflow schedule SCH, the total execution monetary cost of the schedule SCH in cloud computing environment C, we can define it like the WC of the CAH, that is equal to the summation over the virtual machine instances V. That is the V price, virtual machine price of type V, times the provision minus provision time of the virtual machine V by L. So a zero data movement monetary cost among the virtual machine instance, which is the case for cloud service such as Amazon, like Amazon EC2. All of these definitions work for the Amazon too. So any type of cloud computing environment should calculate all of their makespan or workflow cost like this. These definitions round up the virtual machine instance usage to the nearest full billing cycle. So now we can schedule our problem by formulating like this slide. Okay, let's give it a deadline. So now we have a deadline constraint workflow over here. We can define like this. Given a workflow W and an infrastructure as a service computing environment is C, and we have a deadline sigma. The deadline constraint workflow scheduling problem now is to find the optimal workflow schedule SCH optimal that minimize the workflow cost, workflow monetary cost of running workflow W within the deadline sigma. So we can formulate it like this. The SCH of optimal is equal to the workflow cost schedule, which minimizes subject to the virtual machine VMS schedule is less than sigma. Okay, so we need some more definition here to develop some algorithm that we are going to demonstrate over here. So we have the priority rank, we call it PRI of TI, that is the average ETI over the task T if the task T is equal to TT exit. Otherwise, the ETI bar TI is plus the DTT average for the DIJ plus pri of the TIJ, the one that the TIJ makes from the maximum, make it maximum. The TI dot denotes the child task of the TI in the graph, in the task graph. We have the minimum execution time, we call it MET. So for a given, think that we given a workflow graph G and a cloud computing environment C. The minimum execution time of a task TI, we can if the MTI is equal null, it will be is the minimum estimation time between the k between 1 to virtual machine type, the one that for all of the tasks TI over the virtual machine k. That will bring the minimum execution time for the task TI over all of the virtual machine type. And the estimation execution time, we call it E star for the TI, is the minimum execution time if the MTI is null, and if the MTI is not null, we will calculate it by estimation the estimation time of the TI for type MTI. The earliest start time or EST of TI is a function from TP to the TI dot TI, which is the one who maximizes the summation of EST of TP for the task P and the estimation time star TP plus the average data transfer time of the DPI. And the TP is a critical pattern which defines the earliest start time for task TI. So the task TI earliest start time depends on its parent and sub deadline. What is the sub deadline? Sub deadline, we call the sub deadline the LFD. We can calculate the sub deadline with LFD. That is the last finish time. The last finish time of each task within the LFD TI of exit, for example, can be set as a sigma, and the LFD of the other task can be computed like this. For example, for task TI, it will be the time that minimize the LFD of the task TC minus estimation time star of task TC minus data transfer time average of the task DI over the C, from I to the to the task C, and the TI is the here is the child. Ti will be the child over here. Okay, so now we are ready to give our first algorithm. We call it the workflow scheduling algorithm. So the input of the workflow scheduling algorithm is the graph G, which contains the T and E, the task and the edges, and the deadline sigma, and it will be in its output. That is, the output of this algorithm will be in a schedule. So the schedule, at first the schedule set is 0, it is null. The task, we will put the task list in G in descending order with topological priority ranking, that the T list, and we will assign 0 to the estimation to EST of T entry, and compute the EST for other tasks. And we will assign the sigma to the LFT of exit and compute the LFT for the other task. And we will find all PCP's T list, and we will put it in the partial pass. And then we will assign another algorithm by using the pass assignment algorithm. We will pass the partial pass and the schedule together, and then we will have the workflow scheduling time. So all of the algorithm that we are going to define we are going to describe the find all partial critical path function and the path assignment function. So now let's jump into the code here. So this is the planner, this is the algorithm. This algorithm works with this. So in the data view, for each workflow, we have, for example, the workflow. The LPOD is another planner for the workflow. So any workflow planner should implement the plan methods. The plan methods get the nodes parents from the workflows, and then for priority value, it will get the priority value, and it will be sorted. Set the priority values in the sorted map. Then it will build the task time. It will be the task time, and this is the task time. The task time assign the 0 to the T entry, and it will estimate the other time here. Then it will build the. Not only it will build the task time, but also it will calculate the LFT, compute the LFT for other tasks too. Then we will find the partial critical path over here, and we will put it in the PCPs, and after that it will assign it to the PCPs. Okay, so this is all of the scheduling algorithm. So the rest of it is just assigning that schedule for each of this task assignment virtual machine. We will find the TQ sets, and so here we have a virtual machine set, we have a task list, and we have actual assignments, and we have the cost for each pass. And then for each task assignment virtual machine, we will find a link hash map over here. Then we will loop over each of the task assignment virtual machine type, and we will get a local scheduler for them, and we will assign some task scheduler to them, and we will add the scheduler to the L scheduler, and at last we will have our global scheduler here, that we can return it as a global scheduler. So let's jump on the second algorithm. Find all PCPs. In find all PCP, we have a sorted task that is topologically sorted from T1 to Tn, and the output here, it will be a pass list partial pass. The partial pass set is at first 0. And we will loop on each task list that is ascendingly ordered, and at first our CP is equal to 0. Then we will add the TI to the CP. Then we will remove the TI from the task list, and for all of the while TI has children in the task list, we will add the we will put the ti primes, which is the first child of the task list, and in the ti, and we will add this the ti to the cp, and we will remove the ti from the task list, and at last we will add the this critical pass to the partial pass, and we will do it for the other existing task of the task list then, and at last we will returning the partial list. So this is all that we are going to do here in the partial critical pass. Here, find all the PCPs, and now I'm going to over this. So here, as you can see, we have a sorted priority value that are the sorted priority value of the task. We will do 2 loops over them. Here you can see. So so it is at order length. We put it in the task list. We will omit the first one from the task list. We will add and then we will loop. So at first our task pass is we will add a minus integer at the first one as an entry. Then because till the task list is not empty, we are going to find the partial pass for all of the things. Here we have the second loop, that in this method we have a while, and here we have a for each. Here instead of a for each we have a while till the task list has something in it. So at last we will return the partial pass over here. So after the partial pass, we have the pass assignment algorithm. In the pass assignment algorithm, we have it here. So we have a pass list that is like the partial pass from P1 to Pn, and we have as an output we will have a scheduler. We will have a schedule. For each partial pass T1 to Tn in the partial pass, so we will assign the Lj that is equal to 0 for each task in the current partial pass, and let's have that task partial pass has Tn tasks. For each Tj, at first we will assign the false to the found, that the scheduler is not found, or the virtual machine is not found, and then for each of the virtual machine instances we will evaluate that if the virtual machine estimate the available time is less than the EST of the Tij, and the time that is left in the virtual machine instance is more than the estimation time that we need for the task Tj according to the type of the virtual machine type. And again, the LFT of Tj is more than the estimated start time of the Tj. It means the last finishing time is more than or equal to the sum of the EST of Ti plus the estimation time for finishing it. It means that before that this instance is going to be away from our availability, do we have more time to finish the task? So then we can schedule this task schedule it in the T and insert the task into it, and we can assign the scheduler the actual estimation start time, the insert of the Tj to the EST of Tj, and we will assign the AFT to the estimation time to the EST of the Tj plus ET estimation time of the Tj with using the type virtual machine I. Then we are going to add the actual finishing time of the Tj to the with the AFT, and we will insert the in the M function in the M sets. We will insert the task Ti and assign it to the VMI. And the VMI, and now is the time for the virtual machine instance to be updated. So the available time of the virtual machine will be the plus the estimation time of the Tj plus the start time of the Tj on the virtual machine type I, and the left the time that is left for the virtual machine instance I will be the VMI left minus estimation time of the TJ over the virtual machine I. Then we are going to assign the J to the LJ. And now we found a good virtual machine for our task. Now we can go to the other task. Then we break this loop, it means the for each loop. Then we can go to the next loop. Again we will set the found with a false. Okay, at last, if the found is equal to false, after that finish the loop over the task, and we didn't found any virtual machine type here, we will break. And we will use the assign path, and we will pass the TLJ plus 1 to TN. It means from the task that is not yet scheduled, we will put these assign we will call the assign path for the TLJ plus 1 to the TN. And then for each TJ that is belong to the PI, that belongs to the PI, we will put the schedule AST-TIJ in the EST of TIJ, and we will use the schedule AFT of TIJ as the LFT of TIJ. Then we will update the EST for all of the successor of the TJ according to the previous estimation, like 13 and 14, and we will update the LFT for that too. Again, so we will have some time for task that is remained in the PI. So after this update, we can find maybe we can find some other virtual machine type that is exist now. Okay, let's jump into the pass assignment. After that, I will go to the assign pass algorithm. Pass assignment. Again, I will go to the the top of here. Now we will go to we will pass the PCP partial critical pass to the pass assignment. Here it is. So here, as you can find, okay, do not be afraid. It's not a very big deal to know how is it working here. So for all of the pass, as you can see, this 4 is according to the first 4 for each, that is the PI. We need another 4 here. That is the all of the task in the partial pass. Okay, the last level. So the last level, all of it gets the pass size. That is the pass structure that has a string and a list of double, and this list of double consists all of the time that are the AFD, ESD, all of them. So again, for that is the second 4, and again for each virtual machine instances, we have another virtual machine instances, that is the VM that assigned the key sets. We will do it. If it is working for it, let's do it. So if it is not, and we will add the cost, the minimum cost that we calculated to the add cost. And here again, this is after here. This is after here, so we will have this calculation over here too again. So we will have the actual assignments over here. Okay. So here we will use the assign pass. So I didn't describe the assign pass over here, but I will go walk through it. But let's jump into the last part of it. So you will find out what's happening over here. And here, this is the last part. For each of the tasks TI that belongs to the PIJ, each of the tasks TI PIJ, we will append it. We will update the all of the parameters over here. So all of the parameters is going to be updated in this part, task assignment, to see where the edge can be updated to 0. Okay, and Okay, here. This is the last four of the algorithm here. It could be more modular. Maybe in the next version of the data view people are going to refactor this function. This is the last word that is going to estimate all of the new parameters of it. Okay, let's go to the assign path algorithm. That's a big deal here. So assign path. So the assign path, take a path ti to tn, a path schedule that is and return a schedule. And at first the TB is 0 for each of the virtual machine type K. It will create a new tuple nt. Nt is a function from nt to the I that define an ID, that generate an ID for it, and the ntt, that is the T1, and the nttst, that is the boot delay, and the nttft is calculated by equation 16. And the equation 16 is this equation. This is the equation 16, which is calculated by nttft is equal to the nttst plus estimation time of the task ti over the virtual machine type vti. Okay, here. So after calculating all of this, it will insert all of the nt into the nt of the tft if it is less than lft of ti. And for each task, from task, the second task to the last task, for each of the tuple pt of the ti, in the tb that we calculated before in the previous in the tb, for each virtual machine type, it can be created a new nt. And that new nt, if the tft is less than lft of that task, the actual cost will be calculated by another formula that is the formula 18, and the task, the time left for the task will be calculated, and the id reference of the task will be assigned, and the max age will be calculated by another formula, and then we have the tb. Task bench. Okay, so we have here okay. So we will insert it. For the pre-T, we will select all of the from TB all of the T that is equal to the task n, and it will be ordered by the actual cost, and it will limit to the 1. So it will return the first one, and the pre-index will be the reference ID, and it will schedule on the TN. And the schedule, and in the schedule, we will insert the test with the prep and the prep TST, and the actual finish time. The T and actual finish time will be the pret and the TFT. The prep of the virtual machine will be initialized with the new virtual machine of the pre-pret type virtual machine type. And the virtual machine available time will be updated with the TFT, and the pre-virtual machine of the virtual machine left is the pret of the T left, and everything will be updated over here, the provision and the provision of it. And for all of the tasks, inverse form of the task, it means that from the last task to the first task TI, for all of the TB where the ID reference of them is equal to ID, it will put into the current task, and they will schedule from the down to top in the scheduler, and the provisioning and the provisioning amount and the M amount will be updated here. if the virtual machine type is equal to the predicted virtual machine. Otherwise, it will initialize a new instance of the virtual machine, the CT virtual machine, and put it in the current virtual machine, and will again update the available time of the virtual machine, and it will update the virtual machine instance and the provision values. And if the task is not the first task, so it will again calculate the all of the IDs that is equal with the ID reference, and again for the PT, which is the which its virtual machine type is equal to the virtual machine type of the CT, its provisioning time it will be updated. Otherwise, its provisioning time will be updated with the PT TST minus the delay, because it should be transferred to another virtual machine. Okay, if the task is not the first task, so the provisioning time of the scheduler will update with the C virtual machine type and the TST minus the data transfer time, and the CT at last will be updated to the pred. And if n is equal to 1, it means that we are in the first task. Then our provisioning will be updated again for the last time. So we will again reflect the boot delay here. So this algorithm is all developed over, as you can see, from here to yes, from here to here. So all of the path assign path algorithm, and all of this provisioning that we are going to from the size that is equal to here, virtual machine task size will be here again, another 4 for the task size, and this will be another 4 that is so inner 4, all of the 4 that we need for all of the conditions that we need for the provisioning and the provisioning. So again, this was all about the evaluation. So let's go in the evaluation of the LPOD algorithm. So for evaluating the experimental result on the LIGO workflow, the researchers developed a C-score. The C-score is calculated according to the maximum cost. So if the make span is less than the sigma, the C-score will be calculated as half plus half times of the maximum cost minus the cost of the that is spent over here on by the maximum cost. Otherwise, if it is more than the sigma, so the C-score should be less, though it will be half minus half times of the make span minus the sigma. So it means the more sigma we are going to be far from the sigma, the more it will be, the worse it will be. So the make span, maximum make span minus sigma again. So here you can see for this 10 seconds billing cycle for the LIGO, over the they test the 3 different planner for IC, PCP, SGX, EC, E2C, 2D, and LPOD algorithm. Okay, you can see that the green one is the LPOD algorithm over here. That for most of the seconds here it is better, but if you want to see the performance, it will be shown in much more time. So as you can see, in the 60-second billing cycle, it means if the data is bigger and the workflow is heavier, the LPOD algorithm by far is better than the other SGX and the ICP algorithm. Okay, let's wrap up the presentation. In this presentation, we calculate the priority rank for each task. Each measure the longest time passed from the current task to the exit task, and identify all of the partial critical paths PCPs. and then they make the assignment to each path. For the stage 1, a prefix of the path is assigned to the existing virtual machine. In the stage 2, the suffix is assigned to the set of new virtual machines with minimized cost using the dynamic programming. As you see, it means the dynamic programming comes from that we come from the last task to the first task. Okay everyone, I hope that this lecture was beneficial for you. If you like this lecture, just subscribe my channel and tune out. Thank you. Have a good day.